Now moving on to part 3 of the final exam review, which is module 3, titled Two-Dimensional Kinematics. Some of the topics we're going to talk about are vectors, projectile motion, and circular motion. The students that emailed me questions, many of you had some specifically about this unit, and if you gave me a number to those questions, I added it into this presentation. So before we jump into any practice problems, just some equation hints. This was from the projectile motion lab, but it also is a good reminder for thinking about the problems that we're going to solve. So remember, for horizontal projectile motion, you can use these equations. For the vertical, you can use any of these 3 equations. Remember, when you are determining x and y velocity components, some of y'all struggle with this. You're going to use that cosine and sine to figure out that vertical and horizontal components. Vx is horizontal and Vy is vertical. Also, the expected range or distance of a projectile motion can be calculated by using the problem or the equation that you see, but remember that it has to be solved in a quadratic equation as well. Alright, so one of the topics that's covered in this module is uniform circular motion. So remember that it has to meet 2 conditions for circular motion. An object must maintain the same speed, and the radius must be equal throughout the entire path. Tangent and acceleration is always perpendicular, and distance of 1 revolution is 2 pi r. And then t is the total time for 1 revolution. So some of the formulas for uniform circular motion can be seen on the right-hand side of the screen. And there are some practice problems in this module and in the next module for the application of Newton's laws, I guess 2 modules from now, can be solved by using some of these formulas. Alright, so we have practice problem 2, which has moved a little bit. It says, a child rides a horse from a merry-go-round. The horse is 5 meters from the center and goes around 1 time every 25 seconds. What is the centripetal acceleration acting on the child? So my graphics aren't showing up very good here, so I'm going to kind of write them out. First, you're going to solve for velocity. So remember, velocity is distance divided by time. And so we add in what we know about the distance. So 2 pi r is the distance for that circle over t. So that's the formula. So we have 2 pi, and we know the radius, as it states in the problem, as 5. And you're going to divide that by 25. So if we add that into our calculator, we should get 1.26 meters per second. Then we're going to solve for the centripetal acceleration using the formula that we know. So centripetal acceleration is the velocity squared divided by the r. So the velocity squared is what we just calculated above, so 1.26 squared divided by the radius, which is 5.00 meters. Apologize. And we should get 0.32 meters per second squared. Here's another practice problem. It says a boy standing throws a penny horizontal at 7.25 meters per second out the window of his apartment building. If the window is 10 meters above the ground, how far from the base of the building does the penny land? So first of all, we have to kind of figure out what we know, what we need to figure out, and how we can solve this. So the first thing is that we know the initial velocity in the x component, meaning the horizontal component, and that's going to be 7.25 meters per second. We don't know the distance. We don't know how long it takes. We know that the final velocity is going to be 0 because it's going to land on the ground. And then we have a vertical distance at 10.0 meters, but this object is falling down, so now we know that it's in the negative position. We still don't know time. We know acceleration to be the constant gravity at negative 9.80 meters per second squared. So the first thing we need to do is figure out the y-axis for time. So we have the initial velocity is 0 because the boy is holding the penny. We know the acceleration at negative 9.8 meters per second, and we don't know time. So we fill in what we know. We rewrite the formula to solve for time. So we get the square root of 2y, which is the distance, divided by acceleration. We plug in what we know down here, and we should get 1.43 seconds. So that is now time. So we can go back and fill in what we know. All right, so now we're going to look at the x-axis. So we know that the initial velocity horizontal is 7.25 meters per second, because that's what's stated in the problem up here. And now we know time because we just calculated it for the y distance. So we're looking for how far it's going to go in the horizontal distance. So we plug in 7.25, multiply 1.43, and we should get 10.4 meters to the right. That's positive. All right, here's an example of vector addition. So it says add the following vectors: 15 meters at 35 degrees and 25 meters at negative 75 degrees. So first of all, we're going to have to determine the components of each vector. All right, so a lot of you guys get confused. Remember, the x's are horizontal and the y's are vertical. So we have vector A, figuring out both the horizontal and vertical, and then vector B, horizontal and vertical. So again, 15 meters at 35 degrees. So I'm just going to kind of sketch this. Basically what we're doing, this is the y component and this is the x component. All right, 35 degrees. Let's pretend that is 35 degrees. Negative 75 degrees. So you can do that by going below the x-axis here. So we could do negative 75 here. And we have that horizontal and vertical component. So that's what you're solving for right here. So remember, then once you solve for those, it's just the combining those. So we calculate the components of the resultant vectors. So in order to get the magnitude, you're going to plug in 12.3, which is what you got calculated for that A horizontal, plus 6.5, which is the horizontal from the B vector, and we should get 18.8. Do the same thing for the vertical components. You're going to add the two vertical components, and you should get negative 15.5, and then we're going to calculate the magnitude. Remember, the formula is a squared plus b squared equals c squared. So to find the magnitude of that resultant vector, you're going to take the square root of 18.8 squared plus negative 15.5 squared. And if we take the square root of those two squared numbers, the sum of it, we should get 24 meters. And then we also need to calculate the direction because it has to have magnitude and direction. So we take the inverse tan of the resultant vector of the y and the x components. So that's going to be what we calculated up here in this step. So we're going to get negative 15.5 divided by 18.8, and we should get negative 40.0 degrees for sig figs. Remember, guys, the saying Sakatoa, because it helps you kind of figure out what is given and what we need to figure out. Sakatoa is sine opposite over hypotenuse. So if this is the angle, the opposite would be the side directly across from it. Cosine is the adjacent over hypotenuse. The adjacent would always be the side that's attached to the angle. And the hypotenuse is another name for resultant. So tangent over opposite divided by adjacent as well. So Sakatoa, that's what I remember. Helps you remember which sign to use. All right, here's some more practice. So it says a ball is thrown off a 25 meters tall cliff with the initial velocity of 15 meters per second at negative 30 degrees. What is the velocity of the ball right before it hits the ground? So again, figure out what we know and what we need to solve for. So the first thing we need to do is figure out the velocity and the x component and the velocity and the y component. So we know this from those formulas that we were just talking about. 15. That 15 is from that velocity given to us. And then the angle is negative 30. And we should get 12.99 meters per second. We're going to do the same thing with the vertical component. So now we're using sine instead of cosine. And we should get negative 7.5 meters per second. So in the y-axis, we know that it has a distance of negative 25 because it's given to us in the problem. But remember, the ball is being thrown off, so it's falling negative 25 meters. We have the initial velocity at negative 7.5 because that's what we just calculated above. The acceleration is that constant, negative 9.80 meters per second squared, and we need to know the final velocity. So we rewrite the formula, plug in what we know, and solve for negative 23 meters per second. Next, we take what we have of those resultant, a squared plus b squared equals c squared, to solve for the one that we don't know, which is that magnitude or that resultant. And if we take the square root of the sums of the squared of the two sides that we know, we should get 27 meters per second. Now remember that the magnitude is not the only thing we need. We have to find the direction, so we use that inverse tangent formula with the horizontal and vertical components to solve for that angle of the magnitude. So our final example, or final answer, should be 25 meters per second at 61 degrees. And that is it for example problems from this module.